Welcome to the second week of the course Strength of Materials, and in this week we'll be learning about multi-axial systems and stress transformations. So in the previous week, we saw the variation between elastic and inelastic properties of a material. We went ahead plotting and understanding the features that are involved in a stress diagram. We also saw some of the aspects of the term strength. Also came across aspects of strains and their relationship with stress and structural behavior during loading. We looked into the relationship between shear stress and normal stress, and we finally concluded that session with the Poisson's ratio after solving few numericals. So now that we have a better understanding of what stress and strain is, and also we have a better understanding of what are various stresses and strains. So for this week, the table of contents will be as follows. First, we'll start with plane stress transformation, and then we'll be solving few general equations for plane stress transformations, and then we'll also be going through few problems. Then we'll go on solving principal stresses and maximum in-plane shear stress. Next, we'll be seeing about Mohr's circle for principal stress and end this session with absolute maximum shear stress. As for the learning objectives, we will be discussing about stress transformations and its applications. Then we'll see some methods to solve problems based on stress transformation efficiently. Then we'll also come across differences between normal stresses and principal stresses. We'll learn the differences between normal stress and principal stress. We'll go through techniques for plotting Mohr's circle, and we'll also go through some stress transformations for advanced applications. Now let us directly go into plane stress transformation. In statics, stresses acting on a body changes with the rotation of the body due to applied forces. So here, stress is considered positive if it's in a positive phase or positive coordinate direction on the elements. In the same way, it is considered negative if it's in a negative coordinate direction on the elements. So now, what are three-dimensional stresses? In the right side image, if you take this cube is called as the three-dimensional stress element. And the same way, this square which you can see here is called as the two-dimensional stress element. Now this square we have derived from the cube which we have on the left hand side. Now we always know that there are three types of stresses that is acting on this 2D element. Two will be normal stress and one is the shear stress. Here the normal stress or the axial stress, you can call it sigma y and sigma x, and the shear stress that is acting is tau xy. Now, as for the variables, you can only see the notation as y or x here, and because it's shear stress, you can see xy. At the same time, if you see in this 3D structure or the cube which is given, there are different types of stresses that we can see, which is sigma x, sigma y, and sigma z2. So, sigma z is the third plane of stress. And when we see the third plane, we can also come across tau zx and tau zy. Now, if we take a surgical glove, so in the right side, you can see there is a white color diagram inside which there are two boxes drawn. One is a square box and the other is a rhombus. Now, imagine this white color boundary is a surgical glove, and this surgical glove is stretched, and the stretch is happening as it's given in the below diagram. You can see that the square box is undergoing only a change in its dimension, which is length and breadth. So this is basically undergoing a normal stress. At the same time, if you can see the rhombus, it is undergoing a change in all of its angles. So this means that it's undergoing a shear stress. Now, going through all this, the two things which we have to keep in our mind. The first one is the sign convention, which we saw already, which is if it's in a positive coordinate direction on the element's positive phase, it is a positive stress. And it's called a negative stress when it is acting on a negative coordinate direction on the element's negative phase. Now, one more thing is we have to consider the state of stress at a particular angle inside an element at a particular point. Now, if we have to consider a state of stress at a particular angle inside the element at a particular point, which is making a certain angle with the normal or with the x direction. So, if you can see in this diagram, this square is making a particular angle theta with this straight square. So, at that particular point, if we have to calculate the state of stress, we have two methods to calculate it. One is using equation method and the other is using the Mohr circle. Now, we'll be seeing both these methods eventually, and first we'll be going through the equation method. So, general equations for plane stress transformation is what we'll be seeing now. Now, taking a square element or a 2D element, like how we saw back in the slide, we know that sigma x is going to be our normal stress. Same way, sigma y is also going to be the same, but sigma x is going to be in the x direction and sigma y is going to be in the y direction. Same way, as for the shear stress, it's going to be tau xy, which is shear stress. Now, tau xy is in our xy direction, and for a 2D plane or for a 2D element, we'll only get xy because we only have two directions, which is x and y. And also, we should keep in mind that if it's a tensile force, it's going to be positive, and if it's going to be a compressive force, then it's negative. This is our sign convention. Now, if we take the square which is here, this is the orientation which we saw first for our sigma x, sigma y and tau xy. But imagining there is a change in the orientation. So now, after the change in orientation, we are going to call the stresses and tau with a dash, which is sigma x dash, sigma y dash and tau x dash y dash. Now, these are all new stresses. Now that we have taken these stresses from a new orientation, it also means that this new orientation, I'll write it as new orientation, is formed due to an angle theta, right? So, that angle is given here as theta. Now, I've taken this triangle, which is basically the triangle that is formed due to the original element and the new element which was formed due to the orientation angle theta. Now for the equations, okay, we know that stress is equal to force by area, and from free body diagrams and from equilibrium equations, we know that the summation of forces should be equal to 0. This is what is given in the equilibrium equation. Also, if we take a free body diagram as in a triangle, now from trigonometry we know that if the hypotenuse is f, then the corresponding horizontal is sin theta and corresponding vertical is cos theta. So now with that we'll start creating our equations. Now we know the formula for stress, which is sigma equal to f by a. This can also be written as f equal to sigma into a. Now here we have f1. So for all those formulas, f1 will be equal to sigma y dA sin theta. f2 will be equal to tau xy dA sin theta. f3 here will be equal to, f3 is again axial stress, but it's in the x direction. So sigma x dA cos theta, and f4 will be equal to tau xy dA cos theta. Now the two reactions which we need to find are f x dash and f x dash y dash. So these are the equations which we get after we tilt the element of an angle theta. So we know that summation of all the forces is equal to 0. By substituting this formula here, f of x dash will be equal to f1 sine theta, which is here, and plus f2 cos theta plus f3 cos theta plus f4 cos theta. Okay, we'll move to a new page. Now we have all the needed equations here. With that, we'll go ahead. So f x dash is equal to sigma y dA sine square theta plus tau xy sine theta cos theta dA plus sigma x dA cos square theta plus tau xy sine theta cos theta dA. So previously with the free body diagram which we made, we can also get the equation for f x dash, which is sigma x dash dA. Now substituting f x dash equation here, we'll get sigma x dash dA. After substituting, we can see that dA is common for fx dash and the right side equation too. So we can easily cancel out dA in every available equation here. So instead we can write the new equation, which is sigma x dash is equal to sigma y sine square theta plus tau xy sine theta cos theta plus sigma x cos square theta plus tau xy sine theta cos theta. Now that we got this equation, the next thing which we'll have to see is we have some trigonometric equations which we can substitute here. The first one will be cos square theta, which is equal to 1 plus cos 2 theta divided by 2. And the same way we also have sine square theta, which is equal to 1 minus cos 2 theta by 2. There is a third equation which we'll have to take care, which is 2 sine theta cos theta, which is equal to sine 2 theta. Now substituting all these equations in the above formula, sigma x dash will be equal to 1 plus cos 2 theta by 2 into sigma x plus sigma y into 1 minus cos 2 theta by 2 plus tau xy sine 2 theta. We can further simplify this equation to sigma x dash equals sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sine 2 theta. Now we've got the equation for sigma x dash. Now this is for the x direction. The next one we'll be looking at is the y direction. summation of f x dash y dash is equal to 0. Now, due to sign convention and because it's in the y direction, we have some changes in the parent equation, which is f of x dash y dash minus f1 cos theta plus f2 sin theta minus f4 cos theta plus f3 sin theta. Now we have this difference in the signs because if we take it in the y direction, we can see that f1 is going downwards, so it's going to be negative, but f2 is going the other direction, so it's going to be positive. The same way it's for f4 and f3. Also, like how we took the equation for f x dash, we'll take the equation for f x dash y dash, which is equal to tau x dash y dash dA. Now substituting these equations here, tau x dash y dash dA minus sigma y dA cos theta sin theta plus tau xy dA sin square theta minus tau xy dA into cos square theta plus sigma y dA into cos theta sin theta. Now we can simplify this formula to tau xy dash minus sigma y cos theta sin theta plus tau xy into cos square theta minus sin square theta plus tau x into cos theta sin theta. With the help of trigonometric formulas, we'll simplify more in this equation. By trigonometry, you know that cos square theta minus sin square theta is equal to cos 2 theta. Also, sin theta cos theta is equal to sin 2 theta by 2. By substituting these trigonometric formulas in the given formula, we get tau x dash y dash plus sigma x minus sigma y into sin 2 theta by 2 minus tau xy into cos 2 theta, which is equal to 0. Now all these equations are equal to 0 because that is how we define it with the equilibrium equation, which is sum of all forces. So because we have equated all the left hand side to 0, now we can make this left hand and right hand side equation. Tau x dash y dash is equal to tau xy cos 2 theta minus sigma x minus sigma y sin 2 theta by 2. Now this will be our equation for shear stress. Previously we saw the equation for normal stress. Now this will be the equation for shear stress. Now with that we can go into some numericals of the same equation. Now after solving all those equations, we get to this point where we get the equations sigma x dash, sigma y dash and tau x dash y dash. When we take the normal stresses, the only difference between them is that the direction for the first normal stress is in the x direction and the second one is in the y direction. So we only get a directional change which is For sigma x dash, there is a positive note here, and for sigma y dash, we have a negative note here or negative symbol here. Now, we'll just go through few steps for any plane stress transformation related analysis. First one is to sketch the desired surface. If we are given a problem, we'll need to first sketch the desired surface and then mark all the normal stress and shear stress. With that, we'll have to determine the angle from the actual positive x-axis to the normal. Now, this angle is the angle which we mark after we get the orientation of the new plane. After marking this angle, we then draw the rest of the new square and label the positive y dash axis, which is 90 degree clockwise from the positive x dash axis. Then later, using the sigma x dash, sigma y dash and tau x dash y dash equations, which we derived in the earlier slides, we'll try to find the values for all these variables. One main thing which we have to keep in our mind is we'll have to keep applying the proper sign conventions for us to get correct dimensions or correct values of the stresses. So here we are given a very simple problem related to the equations which we just derived. So the statement is, for each state of stress given, find out the normal and shearing stresses exerted on the surface indicated. Now we can see the actual square element here, which has 40 MPa and 80 MPa as its sigma x and sigma y respectively. So the new square which is oriented to 55 degree is also given. With that, we are going to find the values for the normal and shearing stresses. So from the question, what we have is a square element with sigma y and sigma x as 80 and 40 MPa. Now we can term this as sigma y and this as sigma x. As for the sign convention, we can see that this is a compressive stress or this stress is inward. If the stress is inward, then it's negative, and if the stress is outward, it's positive. The same way, if we take shear stress, if the shear stress is in this direction, it's positive, and if it's in the opposite direction, it's negative. So from the question, sigma x will be equal to minus 40 MPa, and this is because of inward direction, and sigma y will be equal to 80 MPa. But because we didn't get any information regarding tau xy, we'll just keep tau xy as 0. Before going to the question, we'll need to figure out a very important value, which is theta value. Now, from the question and from the diagram, we can see that theta is 55. Theta is 55 degree. Now, the stress is acting inwards like this. So, this line is going to be parallel to this line. And if we extend this line with alternate angles, this angle is going to be 55 degree. Now, if we draw a straight line here, then the summation of these two angles is going to be 90 degree. So, this angle is going to be 35 degree. Again, the summation of this angle here is 90 degree. And we'll need to find out, or we'll need to figure out the value of this angle, which is theta, which is the needed theta value. Now, again, we know that the angle formed between these two lines will sum up to 90 degree. So, because of that, this angle will be 55 degree, and again, theta will be equal to 35 degree. So, therefore, we get the value of theta as theta equal to 35 degree. Now, we'll have to figure out the new stresses. So, first, we'll go ahead and directly write the formula for sigma x dash, which is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sine 2 theta. Now because we have not given tau xy or tau xy is basically 0, we can just equate this formula to 0. And with the rest of the formula, we'll have minus 40 plus 80 by 2 plus minus 40 minus 80 by 2 into cos 70 degree. Now by simplifying, we'll get sigma x dash is equal to, will be minus 0.521 megapascal. Now the value of sigma y dash will be equal to 40.52 megapascal. As for tau x dash y dash, we know the formula, which is sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. Now again we can equate tau formula to 0 because we know that tau xy is equal to 0. So with that, by simplification, we get tau x dash y dash, which will be equal to minus 56.4 megapascal. Now, one important thing which we'll have to note here is, even though tau xy is given as 0 here, tau x dash y dash has a value of 56.4 megapascal. And this says that the stress applied even without shear stress is going to create another shear stress when there is a different orientation. So by drawing the new square, which has an orientation of 35 degree, we can say that sigma x dash is inwards and it has a value of minus 0.521 megapascal, and sigma y dash is outwards because we know that the value of sigma y dash is a positive value, so it's 40.52 megapascal. And again, tau x dash y dash is and that's given as minus 56.4 megapascal.